Hi again. Let's see if I can wrap up section 7 today. This grey Sunday. All right, so they want us to look at this curve. Let's just close this one so it doesn't see it. And that's the same as in problem 10. And I believe that the limit procedure will work again. Oops, this map of the complex group. Now. I'm so much in love with the Weierstrass P function that I'd like an approach that looks like it. Will not get the entirely the elliptic curve he states here, but one practically the same. So we define a function from the complex plane into itself, cosecant squared, and then the map from C into the projective space. Z maps to f of z times f, the derivative of f mark. Then we need to find the differential equation for this function. We already have done that before, haven't we? But I'll just do it again. Let's do it on the other page here. So the squared and 4f to the third equals fourth. Oops, I didn't intend to do it in a confusing way, so this is just... the reason I do it this way is because the algebra is very simple and I have a good chance of being able to go through it. So the curve will have this equation so we have a curve in here. Oh, it should have been here. So that's the image. Was it -1? Yes, it was. So, well, I don't care about that really. Now we need to prove the addition law, and I hope it will work the same way. So we are just, well, first of all, this function is periodic with a period pi, so I would like to have it go from minus pi half to pi half. So that's the slices I would like to use. And continuing all the way through modulo pi. So that's our lattice. And then we should now what should we look at? So if you have 2 points on this curve, we would like to see that the line through it goes through another point. That means that every line will intersect it three times, but that's Bezout's law. So we need to show that the sum of the set solutions to the equation of intersection has the sum of them vanishes. So that's the same way as we did it in the section. I've just forgot about it in the meanwhile. So the equation is y minus mx minus b, and that means we define the function. Y is the derivative. There's a minus ahead. So we'd like this function to have, or like to prove that the sum of the solutions in this strip vanishes. So we need to make the integral along this line, and the path integral around here will vanish because the integral this way equals the integral this way. It's periodic. So going around here, then the vertical strips will vanish, and whatever function we use. But to prove what the sum of the solutions is, we have to look at z, the derivative of g divided by g. And that becomes complicated That was so easy in the last exercise, so I'd expected it to be just as easy. You know what? I take a break and plug it into Mabel, and then we'll see what it becomes, and then I'll see if I can do anything with it. So back again. So I typed it into Mabel and differentiated and constructed this function, and z times its differential divided by the function. And then the sum of the residues should vanish, and I can't see that. I have no clue how I should analyze this function. But then on the other hand, maybe we don't have to. If instead we integrate it from 0 to pi, or use the strip from 0 to pi instead, then maybe it should be nice. We might have some poles, of course. Now the question is, what could go wrong here? Because I can't prove that any function, the sum of the solutions to any function vanishes. So there must be something special about this function that causes it. So I'm missing something here. All right, so I can't do this. That means I have to fall back to the limiting procedure, like the one I worked out in problem 10. But then we need to find a map from here into C, so that the map going from Z over here is E times 2I Z, 2I Z, yes. And we have that Z maps into so if we take 2x and add here, then we get cosine plus something sine. So we just have to multiply this by minus 2i. So that is minus, what we'll call this map H. So this is what we want to get. So it's cosine plus E sine, I sine. So it's minus 1/2 y plus I x. And then we have sine to the third in the denominator. So we have to make 1 to make it cancel. So here we should have the complex conjugate in a way. And what do I do here? I multiply both the denominator and numerator with -2. And then we just use Mabel to check that it's right. So we have these two. I've already forgotten it. Y minus 2ix. Oh, I think we should convert it to exponential. Ooh! Success! So that worked. But proving the addition law using complex function theory, that was beyond me right now. Maybe I'll make a follow-up where I do it. But I have to admit that I couldn't do it right away. So that stops the first recording. Back immediately. I just remembered that. Does this help? It's a poor light. That's worse. Well, maybe the webcam can get used to it. All right. I had to show. There was one problem I had to do. We should draw the graph, show where the various sections go under. So there's a singular point at naught and a singular point at 1. Or maybe that's not singular. Oh, I totally missed this. So this is always positive, so it has to be x equal to, if x different from 0. So it has to be larger than x. So I believe we get a curve like this. And of course with a vertical tangent here. And now if we go back, where does it come from here? I believe it comes from the interval from, it's 1 divided by sine, so let's say it comes from here. And this maps to infinity. They both map to infinity. No, that's false. I'm thinking about cosine, the 1 divided by cosine squared. So sine, once again, this is infinity, then it goes down to unity, and then at pi it's infinite again. So this is the interval. And here it's a decreasing function, so here it's negative and here it's positive. So that means that if we go from here to here, then we'll go from upwards here, and then at 1 at pi half, we will pass through this point. And it maps to so we have Z being real. It goes from 0 to pi. So that goes around the unit circle. Once around. So here we start at 1, infinity maps to unity, and then this one maps to -1, and this guy here maps to infinity, maps to 1, one time around the unit circle. Once around the unit circle. We just need to check that 1 comes from pi half. Pi half goes to -1. Yes, everything's fine.